Welcome, everyone. I'm very happy to announce the speaker for our first CRM Applied Math seminar this semester. And the speaker is Stephen Becker from University of Colorado in Boulder. And he's an expert in optimization, machine learning, imaging, signal processing, and many more areas, and especially at the interfaces of all these different areas. And Stephen got a PhD from Caltech under Emmanuel Candes, and then he went on to do a postdoc in Paris, très bien, with Patrick Combet. And then he had a second postdoc stint at IBM Research, if I'm not mistaken. And then in 2014, became an assistant professor in Boulder, where he still resides. And we see that beautiful picture of the campus. And yeah, so Stephen, I'm very happy to have you. And so the stage is yours.
Okay, thanks very much, Tim. So I guess if you want to ask questions also, I think that would be okay, although maybe it's easier to save them to the end.
Yeah,
you always chat or something.
Yeah, maybe just write questions in the chat during the talk, and then we can decide if you want to react right away or if we save them for the end of the talk.
Okay, so yeah, so I'm going to talk a bit about machine learning and some analysis. This is joint work with my student Liam and my colleague Emiliano. So let's see. Okay, so I want to start with something you might have heard of, Hilbert's 23 problems. So he announced these in 1900, 120 years ago in Paris, 23 problems that were unsolved and he thought would shape the future of math. And they did shape the future of math. So for 100 years, mathematicians tried to solve these, and they really influenced a lot the direction of math. So extremely influential. So some of you, I think, have probably heard of these. What you might not have heard of is there's actually a 24th problem. So Hilbert he only presented 10 of these in orally, but he wrote the other 23 down on paper. He had a 24th one he thought about including, but decided not to. So a historian found this 20 years ago and published about this. So that's not so well known. What's even less well known is his famous or infamous 25th problem. This is the problem on the classification of dogs and cats. It was only discovered very recently by computer scientists. So a hidden problem, but very, very important. Hilbert thought this was one of the most classical problems there is. So putting it into sort of modern mathematical notation, the question is, can we find a way to distinguish a photo of a dog from a photo of a cat? And I know what you're thinking. You're thinking, obviously, this is impossible. No one could do this. It's an unsolvable problem. It turns out you can do it with enough math. In fact, the Babylonians could do this. We don't know how, but we have evidence that they did this. The next innovation, the Industrial Revolution, parallel processing, they had a very nice algorithm. They called it children. You take an image, give it to a child, and they classify it as a dog or a cat. Okay, so this was revolutionary. Accuracy went way up, but of course there's many downsides to this. The next big innovation, 1989, we invent the World Wide Web so we can store these photos of dogs and cats. And then finally, coming closer to today, in 2012, deep learning comes up. We can classify billions of images of dogs and cats and solve all our classification of dogs and cats needs. Okay, so this is a silly example I made up. There is no 25th problem. There is a 24th, but not a 25th. It's because I go to all these machine learning talks. I go to any talk, and most talks these days have some kind of machine learning element in them. And then they motivate machine learning by talking about classifying dogs versus cats, which is a very silly example because a child can do it, all right? So I'm kind of pointing out that it's a bit silly, but machine learning nevertheless is super useful. Whether you like machine learning or not, it's here. We have self-driving cars. We have machine learning algorithms making decisions for judges, for sentencing, extremely important things. So that lets us ask the question, is there math behind deep learning? Is there a theory behind this? And the answer is yes. I'm assuming most of you are not computer scientists. Computer scientists know about this. Since about the 1980s, we have a fairly good theory. But it's not a complete theory. Do we understand everything there is? And the answer is no. The theory we have is loose. or there's certain problems with it. And I'll talk about that in this talk. This is sort of a dominant goal of many, many researchers these days. So we'll talk about some of these things. So let me tell you what we're going to talk about in this talk. I'm going to spend a while going over the background of sort of what's been known, existing results in the classical theory. And then I'll talk about the shortcomings of that. Then we'll talk about stability, which is a new framework. Well, it's not that new, it's 20 years old. But about 5 years ago, it was sort of revitalized. And that's sort of the approach I'm taking for some of my work. So I'll try to make that clear. The background here is what I would call textbook material. So it's standard. If you took a theoretical machine learning class in a computer science department, you would learn about this stuff. But for me, at least from my applied math background, this was not something I learned in grad school. It's not something I learned in any kind of course. So for me, this was very new. And some of you may know this already, but I think it's maybe interesting for applied mathematicians to sort of see what our colleagues in computer science have been up to. And the whole time, we're trying to answer this question: why does machine learning work as well as it does? Okay. So let's state the problem. We're going to talk about statistical learning. So we're going to have some features X. This is something like a picture. It could be a picture or an email, something like this. And we can either think of it as like a vague instance or parameterize it with actual numbers. So it could be a picture, or it could be the pixels in the picture. It could be an email or the actual words in the email. And then we're going to consider supervised learning. So we get these labels Y. And Y is something like, if it's an email, Y could say whether it's spam or not spam. Or if X is a picture of a dog or a cat, Y would be maybe 0 for dog and 1 for cat, something like this. Okay, we're going to often group X and Y together into Z, just for convenience. And then our main assumption is that Z is stochastic. So we're going to observe Z. It comes from some distribution D. So D is some arbitrary distribution. The environment chooses the distribution D. And we don't know what the distribution is. So the main points here is we're going to see observation Z. So we're going to have a data set S with M observations. We're assuming these are IID observations. That's our big assumption from some distribution D, but we don't know what the distribution D is. So it's not Bayesian. In Bayesian, we would say, we know what this distribution D is. We're assuming we don't know that, but we are assuming there is a distribution, and we're getting IID samples from this distribution, okay? We're gonna have M training examples that we see, and our goal is to be able to learn something about these with M as small as possible. Okay, so this is sort of the environment. Now, what do we do? What's our job as a learner? Our job is to choose a function H. So if you're doing a classification problem, you could call this a classifier, or it could be, something for regression too, but it's some function between X and Y. So you give me a new instance X, like a new picture, and then my classifier will tell you whether it thinks it's a dog or a cat, or whether the email is spam or not spam, okay? And then these H live inside this capital H, not a Hilbert space, just a collection of these classifiers. Okay? When we start to talk about details, we're not going to talk so much about H, we're going to talk about W. We're going to parameterize this by W. An example of what, how this looks like, think of a regression problem. We have a linear function. So I'm going to try to find a W, which parameterizes my H. You give me a new point X, and then I predict the Y value by taking the inner product. That's one example. It could be something like the same thing, except I take the sign. So this would be used for classification problems. Or we could do neural nets. So maybe then the weights are what we parameterize it by W. And then H would be the set of all neural nets of the appropriate size and shape and with the same activation function. Now, if you like, you can include some of these hyperparameters like the topology of the neural net inside the weights. It doesn't really matter for our purposes how you think of that as either part of the set H or inside the weights. Okay, so our job is to find an H. How do we evaluate how well we do? We need some kind of metric. So we're going to take a loss function. Because we think of it as a loss function, it's usually non-negative. And often there's assumptions that either it's bounded or Lipschitz continuous. Those are standard assumptions. So the most common examples would be for classification is this 0-1 loss, which just tells us how many times we got it wrong. So we make a prediction, and if we get it wrong, then we pay a cost of 1. Otherwise, we don't pay any cost. Or something we're all familiar with, just the regression, the usual least squares term that's used for regression. So we can choose a loss function here. And then a question you might come up at this point is, I told you it's not a Bayesian framework. So our distribution D is arbitrary. So if I give you an arbitrary distribution, your first instinct might be like, how on earth could I say anything about an arbitrary distribution? It has unbounded support. I don't know anything about it. Well, it turns out that's okay because it's going to pass through the loss function. So as long as we have assumptions on our loss function, things are going to be okay. In the extreme case, our loss function is constant, and then it doesn't even matter what our distribution is. In a slightly more realistic case, our loss function is bounded, and then we can still use powerful tools like Bernstein's inequality, which only, the only requirements for this inequality is that we have bounded variables that are centered and that are IID, okay? In fact, they don't even have to be IID, they just have to be independent. So we will fit this kind of assumption. So there are things we can prove as long as we have, enough assumptions on our loss function L. Okay. And then from this little loss function L, we're going to make our true thing we care about, the risk. So the thing we ultimately care about is this true risk term right here, which means if I take a Z from this sort of underlying distribution, what's the expected loss I'm going to pay with my classifier or with my function H? This is basically the same thing as a testing error you might have heard of. And then we're also going to use this tool here, the empirical risk. So remember, I have this data set S. So from this data set, I can make this empirical risk, which looks like the true risk, except it's now sort of putting a uniform distribution on the actual observations. So this is what I have access to. This is the training error. And so I don't really care much about this itself, but I'm going to use it as a proxy for the true risk. Okay, so this is our setup. This was just one possible setup for machine learning. This happens to be supervised learning, and there's a lot of other assumptions in there. There's many other interesting cases, but we're simplifying to this case because it's sort of the simplest case where interesting things happen. Okay, so my goal as a learner is to find some algorithm or define some classifier H, and I'm going to find this in an algorithmic way. So I'm going to have some algorithm, which is A. For the whole talk, A is going to be some algorithm. And then S is my input data, my training set. So given my training set, I do something on the computer. It gives me a classifier. And I want this classifier to be close to the minimum possible I could do outside of my set H. Okay, so that's my goal. And one of the standard tools we're going to use is empirical risk minimization, or ERM, where I say, okay, I can't actually see this true risk because I don't know what D is. So I can't evaluate that. But I do have this empirical risk. So let's minimize the empirical risk and hope that it generalizes to this true risk here, okay? Now, you have to be careful. We don't want to memorize the data set. We don't want to overfit and so on. So we'll talk about that in a bit. And then the way we phrase the problem, so our setup is learning theory. And then this PAC, the PAC, probably approximately correct framework, is a way to quantify whether we can learn. So it says the following. It says, we say a problem for a fixed class H and a loss function L is PAC learnable if for any tolerance epsilon and probability of failure delta, there's some M and there's some algorithm such that for any distribution, as long as I have enough samples M, then the true risk of the output of my algorithm is within epsilon of the best you could do. Okay, so this is our reference quantity right here. This is sort of the best you could do, even if you knew what D is. So if you have a Bayesian who knows what the distribution D is, this is what they would get. We don't know what D is because we have to choose the algorithm before we see the distribution. Okay, so it's a harder task, but we are going to allow us to take as many samples as we need. Okay, so if you can do this, if there is a finite M such that this is true, then you'd say you're PAC learnable. So PAC sounds kind of fancy, but it's something we do all the time in applied math, right? Just think of a confidence interval where you have the width of the confidence interval, which is like our epsilon. And then if it's a 95% confidence interval, that would be your delta. Your delta would be 5%. Okay, so it's a very similar concept we do all the time in applied math. Okay, so to be pack learnable, it means that this M must be finite. In particular, this capital M depends on epsilon and delta. So we require that this is finite for all epsilon and delta. It's independent of our distribution D. And then sometimes implicitly or explicitly, we want this thing to grow not too fast in 1 over epsilon and 1 over delta. So usually polynomially, so that typical results look like this. And then if we're lucky, we get also something like this, so that delta can be extremely small and we don't pay a large factor. Okay, so that's our goal, to show that something is pack learnable. Here's our definition of pack learnable. Is this possible? And in the 1990s, Wolpert and colleagues proved that in some sense, this is not possible. They had this no free lunch theorem. They're specializing to binary classification with a 0-1 loss. Let's say I have an infinite set. If you fix any algorithm, and suppose you let H to be the set of all measurable functions. So I didn't say what H is. I said, we can choose H. Suppose H is as large as we can let it be. If it's as large as possible, then things are not going to work, because then an adversary can find a distribution D that has such that there is some function H that has 0 true risk on this, but whatever we output with our algorithm has a risk at least 1/8 with at least this probability. So it means we can't drive delta to 0 and we can't drive epsilon to 0. Okay, so this is kind of disappointing. It says this is impossible. For an H like this is impossible. So let's interpret this. What it means is I can't choose H to be all measurable functions. I'm going to have to pick a strict subset of these functions. And so when I do that, I'm really encoding prior knowledge. So it means that if I chose H to be all possible functions, that would be like a universal kind of problem. And what we're saying is that that's not possible. I can't have this kind of universal learner. But if I can choose H, if I can restrict H a little bit and say it's not all functions, it's all continuous functions, or it's all piecewise linear functions, or whatever H might be. When I restrict that, that's encoding prior knowledge, and now maybe I can learn. But the trade-off is that my reference term, this bias, might be larger. Okay, so in order to choose this bias to be small, I want to have a wise choice of H, and that's what we call our prior knowledge. I'm using maybe expert knowledge to do that. So, if I do this for email classification, if I choose H wisely, I'm really using this fact that I know something about email. So I'm coding this extra information in there. And what these no free lunch theorems say is that that's necessary. You can't let H be all possible things. Okay, so we've agreed that H can't be everything, but maybe now if it's not too complex, are things possible? A very simple example, suppose I restrict H to be just constant functions, and I have a squared loss, then my ERM estimate would be the sample mean. And I know with enough samples, by the law of large numbers, the sample mean will converge to the true mean. Okay, so that means, with enough samples, this thing is possible. So that gives us some hope. And we can be a little bit more specific. We can talk about measuring, we don't want H to be too large or too complex. So how do we measure size or complexity? There's some standard tools. One way is this Rademacher complexity. So I take a family of functions F. I'm thinking of F as like a loss function composed with our actual classifiers. And what I'm going to do is I'm going to take a random variable sigma. So sigma is a Rademacher random variable. It's plus or minus 1 with equal probability. And so I have these values sigma. And then I'm going to take F. F is kind of like a classifier with a loss function. And I'm going to apply it to my data points. And so I'm going to say, how well can my labels predicted by my classifier correlate with these sigma? And so what we're doing in sort of plain words is saying, how well can my output correlate with random noise? Or in other words, how well can it explain random noise? And this is a bad thing. You don't want to be able to explain random noise because then you would overfit to noise, okay? So we want a small Rademacher complexity. We don't want this to be too large. There's different notions of Rademacher complexity, but both of them give us useful bounds, right? This is just the expected value of this quantity here. Another standard tool is this VC dimension. So it's sort of developed in 1971 and really applied into theory around the 1980s. It's specific for binary classification, though there are certain extensions. To introduce this, we're going to think of a growth function. So the growth function for my set H is a function of M where if I have m points x, so x1 up to xm, how many different ways can these be classified? Meaning, if I look at all possible labels on these points, so I'm doing binary labeling. So if it's binary, there's m points. Each one can have a label of 0 or 1. So there's 2 to the m possible labels. So this thing is always less than 2 to the m. And my question is, when does this growth function equal 2 to the m? Okay, so I'll introduce some notation. If I have a data set X, then if I have, if for whatever labels I want to choose, if I can find a classifier that explains those labels, I would say this set is shattered by my set H. Okay, so if I can explain any possible labeling, so you pick these data points, and then if there's, no matter what the labels are, if I can explain that, then I say it's shattered. And this is a bad thing, right? I have this quote down here: a theory that explains everything explains nothing. If I can explain all possible outcomes, then I can't possibly have any predictive power. It's not falsifiable, right? So I don't want to be able to do that. So I don't want to be able to shatter all these points. And VC dimension is the maximal size of a set that can be shattered by H. So here's an example. In 2 dimensions, consider H being the set of all affine classifiers. You could think of this as being parameterized by 3 parameters, a unit normal to a hyperplane, and then an offset to the hyperplane. So 3 parameters. And if I have a data set with 3 points, no matter how I choose these labels, so my labels I'm representing as minuses and pluses, if I make these all pluses, I can choose a hyperplane such that they're all on one side of that. Okay, so I can explain all the data. If I choose 2 pluses, I can draw a line between them and explain that. If I drew it like I did here, here's a line that explains that. So I can explain all possible things, so I can shatter that set. When I go to 4 points, it turns out that no matter where the x values of these 4 points are, I can't explain all possible labels. So you can't prove this with pictures quite the same way because it's for all possible locations of these. But you can see that for these 4 locations, if I put on this pattern of labels, I can't separate these with a hyperplane in a way to get all the pluses on one side and all the minuses on the other side. So that set is not shattered, and in fact, no set of size 4 is shattered. So the VC dimension is 3. Okay, so those are notions of complexity. And now putting these things together, we have what this textbook calls the fundamental theorem of PAC learning. And it says, if your VC dimension of your space is finite, then my sample complexity is finite, and hence we're PAC learnable. And furthermore, I can achieve this by using the empirical risk minimizer. Okay, and then there's variance with Rademacher complexity that look a little bit different, but essentially that's another way that gives you a similar kind of theorem. Okay, so to summarize, if you have a bounded VC dimension, then you can prove that you can solve this PAC learning problem. Okay, now I lied a little bit. I said we want to do this. We want to make this thing within epsilon of this this sort of reference here, right? Well, that's not really true, because I could just make this h to be very, very simple, very, very small, and then this term gets very large. I really just want this thing to be small in general. So I want this thing to be small. So if I want that, I can then separate this into 2 parts. I'll write it as subtract off this minimum and then add this minimum back here. And so now I can say, this is what I'll call the estimation error, and this is my approximation error. And the general rule of thumb is that we have a trade-off. As my model H gets more and more complex, if it gets more complex over here, that means I have a larger set H, and this minimum gets smaller and smaller. So I have this error that goes down like that. I can explain more things, but the larger H is, the less I can generalize. And so then this estimation error is going to get larger. So here I get larger and larger and larger. I've overfit to noise, and I can't generalize as well. Okay, so we have this, what we call a bias-variance trade-off. Same thing you've seen in other subjects. It comes up a lot. Just, we teach this example, like if I have 5 points and I want to interpolate these, it's probably better to do a straight line fit than to find this degree 4 polynomial, because the degree 4 polynomial overfits to noise. And if you want to extrapolate or something, say to a value over here, I'd much prefer this linear fit, which has high training error, but very low but you know, it somewhat generalizes as opposed to this overfitting thing, which has very low training error, but can't generalize at all. Okay, so let's go to deep neural nets. A lot of machine learning these days focuses on deep neural nets. What do we know about them? Well, it turns out they are expressive enough. We have what I call an analog of the Weierstrass theorem, the, you know, the classical theorem about approximating continuous functions with polynomials. There's an analog for neural nets, which says the following. If I have a compact set K and a Lipschitz continuous function on that set, then there is a neural net that approximates this up to any arbitrary precision epsilon. Okay, so that's very nice. I can approximate things. You can make more quantitative versions of this. You know, here are some recent results where I have, you know, if I want to have this precision epsilon, I need this many layers and this many weights. And then you can also, you know, prove lower bounds on this and so on like that. But overall, this is good news because it means that my approximation error, if I use H to be all neural nets, is small. Okay. What else do I know? Well, I know that neural nets are not too complex. So the VC dimension is not too large. I can bound it. Here are some recent results saying that, you know, I have a very good bound on how large this is. It looks like the size of the edges times the number of layers times some logarithmic factors. Okay, so I know that this thing is not too large. So that's good. So that means, therefore, I can bound this estimation error by using my theorem. Okay, so both those terms are small. I can bound those two. That's very nice. Now, the question, so therefore, haven't we solved everything? And the answer is no, we haven't quite solved everything. One issue is that my path learning theorem assumed I used this ERM solution, the empirical risk minimizer. But that thing is generally intractable. So for neural nets, finding this minimizer is solving a non-convex problem, and I can't solve arbitrary non-convex problems. So that thing is intractable. Furthermore, if I plug in the actual numbers for the sample complexity that I would need, I would get a huge number of samples. So in practice, you know, I might need millions of images to do this effectively, but our theory might predict, you know, billions, trillions, something that's much worse than I actually have in practice. So it's not very quantitatively sharp. And furthermore, it doesn't explain comparisons between different methods or strategies. Like often when I train things, I don't run a lot of iterations. I stop early because I get better generalization. So this can't explain why that would happen. Or why one architecture of neural net might work better than another. So it's not tight enough to be able to explain what we see in practice. Okay, let's also talk about what we do in practice. So there's theory and practice. In practice, it doesn't matter so much what your VC dimension is. We do things differently. So we take all the data we have and generally split it into 3 groups. A training group, which we use for our empirical risk term here, and then try to find a minimizer of that term. So that's our training set. We might do an iterative algorithm like stochastic gradient descent or something. So we iterate along and we get our training error to go down and down and down and down and down. But then if we keep training, often H is too large and we can't generalize. So we use a validation set to check when this starts to go back up. So it might flatten off or even go up, and that's when we stop the algorithm. So that's what our early stopping is. And then we have a testing set, which is what you report, say, for a paper or something like that. And this is a true proxy for the true risk. You don't need a lot in your testing set because if you really do it properly and the samples here are independent of what you learned H, meaning you didn't train on those samples, then this thing concentrates very, very quickly. So you don't need too many testing data points for that to be true. Of course, that's assuming, you know, you really do have IID samples, which may not be true in practice. Okay. So, you know, what's wrong with this setup? Well, or what could we do better? Well, for one, this is a very much like a posteriori kind of bound. It's a guess and check kind of method. So, you know, it would be nice if we could have an a priori bound, some kind of predictive bound, or so it could say this algorithm is going to be better than this other one, or explain why a method works so that we can make better methods in the future. You know, currently we run lots of these simulations, and they do take an actual, you know, physical amount of energy. So it'd be nice to keep this down smaller. Other reasons, you know, it'd be nice not to have to use this validation and testing setup, because while theoretically, if you only use those once, they work very well. In practice, we start to kind of train on the validation set. It sort of creeps in there because anytime we rerun an experiment, if we rerun the experiment and use the results of our previous experiment, or do all the experiments and take the best one, then really we've trained on that validation set. And it's very subtle and it's easy to creep in there. So it'd be nice not to have to do this. So these are some reasons why this current framework could be improved. Okay. Now I talked about how are things done. Let's talk about how we actually train. So how do we actually train to solve this empirical risk minimization framework? So recall, here's our empirical risk defined as this. It's the loss on our training data. From now on, I'm not going to think of it as H. I'm going to think of H as parameterized by W. So something more concrete, something finite dimensional. And I'm going to turn this loss function, I'm going to sort of embed this I into the loss function like this, Li, okay? So this is what I care about. This is my empirical risk term. I want to minimize this. And the standard way people do this is stochastic gradient descent. We call it descent, even though it's not a descent method, but it's just very common terminology. So we'll call it SGD, or stochastic gradient descent. And it's fairly simple. We iterate up to capital T iterations. At each iteration, I draw a sample I from all the possible training examples. And then I form my gradient estimator G, which looks like the gradient of this term here, except I don't have all the terms in the sum. I only have the terms that I sampled. And then I normalize it by the size of the things I sampled. Okay. So in the extreme case, B could be one element. But in the other extreme, B could be everything, and then it's not stochastic anymore. Now, when people say stochastic methods, you don't have to have it in this framework, but this is probably the most common framework. And the way we wrote it down here, it's very clear that conditioned on all the prior things in this filtration here, this thing is unbiased, an unbiased estimate of the true gradient. Okay. And then once we have this stochastic estimate of the gradient, we just iterate with a step size eta. Okay. So this is stochastic gradient descent. It's the workhorse of training neural nets. Of course, there's many variants, but this is sort of the heart of the method. Okay, so let's review, what do we know about stochastic gradient descent? What kind of theory can we say? So this is some theory from this nice review paper. This is a very nice paper because it's written by machine learning people like Leon Botou, but also with Frank Curtis and Jorge Nosadal, who are very much in the optimization community. So it's a nice mix between machine learning and optimization. And so a typical result says, if I assume something like, suppose I have this smoothness condition, meaning my gradient is beta Lipschitz, a very common condition in optimization. And let's assume we're bounded below. And I have a bound on my stochastic gradients of a form like this. And you can enforce this in different ways. We're not going to talk much about this kind of assumption in this talk. This is sort of, there's a lot of papers examining what the appropriate assumption for this look like. But for now, we're not going to focus on that. So then a typical theorem says, if you fix the step size, so eta is in this range, then this quantity is bounded by these terms here. This term goes to 0 as I take more steps, and this term never goes to 0. So if I want this thing to be small, I need a small step size. I can make it arbitrarily small, but then I converge more slowly. So there's this trade-off, which is annoying. Or I could force my step sizes to decay, not too fast, but it should decay to 0. So the classical example is just the harmonic series. Then I can prove that, in fact, this gradient goes to 0, the limit goes to 0, or the actual limit goes to 0 under a few extra assumptions. Okay, so these things are all about either gradients or averages of gradients. And you can tell right away, these are not that strong of results. Because saying the gradient is 0 is not that useful. All it means is we have a stationary point. And that's the best we can do in general. But it will be nice to say we have a local or global minimizer. So that's generally not possible without more assumptions. We could add more assumptions like convexity or strong convexity. So let's see what happens when we do that. If I have strong convexity, that implies these two conditions here. The first one is we're going to talk about later. It's called the Polyak-Lojasiewicz condition, the PL condition. And the second one is this error bound condition. So it implies both of these. But now from these, you can see right away, if I can show that my gradient goes to 0, so then the right-hand side goes to 0. Therefore, the objective value converges to the true objective value. And my iterates converge to the true iterates, okay? In fact, the way we converge, I would say that we converge in L1 and we converge here in L2 or quadratic mean. Let me just review that very briefly in case you're not familiar with that. So if I have random variables, there's many different ways random variables can converge in distribution and so on. So the ways we're going to talk about are the LP ways. So here's for p equals 1, you have this thing equals 0, and we write it to look like this. You could converge almost surely, which says that the probability we converge is 1. And then there's a weaker notion called convergence and probability. And a standard fact is that both L1 and almost sure convergence imply convergence and probability, but L1 and almost sure convergence neither implies the other. And there's examples like in this case where you converge in L1 but not almost surely. So almost all results that you see in machine learning that look like this, they talk about convergence and expectation. So this is L1 convergence. You know, there are some results that are almost sure, but most things are L1 convergence. So now we can ask, what can we do beyond L1 convergence? Because L1 convergence is a bit weak. It doesn't control the variance. It says we converge in expectation, but it doesn't give us a nice bound on how likely it is for their deviation to not be there. Okay, so we'll present a result that's stronger. We'll assume strong convexity. And now things start to get complicated. So as we add assumptions, if we have strong convexity and our function is Lipschitz, those two things are only possible on a bounded set, or if your function is a constant function. You can see that because strong convexity implies this error-bound condition. Lipschitz continuity, if you're differentiable, means your gradient is bounded by some constant, we'll call it rho. So if your gradient is bounded, plug that in right up here, and immediately you see W is bounded in some radius around these other points. Okay, so you're in a bounded set. And that's a big assumption. So these things are sometimes assumed and not really thought through. People just add assumptions on, and you have to be very careful about, sometimes they contradict each other, or they can be vacuous, or require things like that you're on a bounded set. Furthermore, when we talk about neural nets, if we talk about binary classification like a 0-1, that's clearly not a Lipschitz function. And even if we have a nice loss function, the neural net itself is not strongly convex and so on. So I would say from this point out, we're going to add more assumptions as necessary so we can prove things, but our assumptions are less and less realistic. Another issue we have is stochastic gradient descent is not a descent method. So our last iteration is not necessarily the best iteration. So do we take the last iteration? Well, there's other things we can do. One thing you could do is sort of evaluate your objective function and see which iterate has given you the smallest objective function. But that's actually impractical because usually we have so many points, we can only do a stochastic estimate of our function. So that's expensive. We could randomly pick an iterate, or similarly, we could average all the previous iterates, or just average the most recent iterates. So these are sort of theoretical devices that people often do when they prove things, although in practice, just choosing the last iterate is probably the most common. Okay, so here's a result I'm going to present. It's from this recent paper over here. And it says, assuming this Lipschitz continuity and strong convexity, so again, either we have a constant function or it's on a bounded set, then the norm of the gradient is bounded with probability 1. Again, not too surprising if we're on a compact set. And then for this given step size that diminishes, I have this nice high probability bound. So it says I decay like 1/t with a small logarithmic factor. And I have this nice probability. So delta could be very, very small, but because it's a log of 1/delta term, it plays a very small role on the convergence. Okay, so I call that a high probability result in contrast to maybe a fixed probability result that you use with like a Markov or Chebyshev inequality, where it depends on 1/delta. So you can't make delta too close to 0 or this starts to blow up. And this is often the case if you see a result that says with probability 0.9 or something like that, it's often because they have this bad dependence and so they're hiding it by doing this. Okay, so that was sort of an overview of classical theory and what's done in practice. Now let's talk about this notion of stability. So I said, I'm trying to motivate, there's something to fix. We want a more useful theory. And there's many different ways to do that. A lot of people are working on that. And you know, I can't really tell you about all these different approaches, but one of these approaches is this approach of stability. So I'll talk about that. It's not that new of an approach. As I said, it comes from about 2002, but very recently, there's been more work in the area. So let's just refresh, since it's been just a few slides, our notation. I have data X with labels Y, and I put these all together into Z. I get IID observations of Z. I have M of these. I'm trying to find a classifier, and I really care about this true risk, and I have access only to my empirical risk as a proxy for the true risk. So let's now talk about stability. We're going to talk about algorithms being stable, just the way you would in a numerical analysis class. So we talk about stable. It means, you know, that you're not too sensitive to changes on the input. The difference is that traditionally stability is more in a continuous limit kind of sense. We're not going to be continuous in that same sense. That's the main difference. It's going to be more discrete of a difference. The main proofs are not that difficult. The big thing is that we're changing how we're going to think about the problem. So before, we think of an algorithm A might be the minimizer of the ERM problem. And that's kind of abstract. And furthermore, we often can't find that if it's non-convex and so on like that. So that's the old way of thinking. And then if we want to stabilize that, we might say, instead of minimizing the empirical loss, we could minimize a regularized empirical loss. So, you know, the same thing we do in other fields of applied math, we add on some regularization. Okay, that's the old way. In fact, the first stability paper from 2002, you know, talks about this kind of regularization. Then now the way we're going to think about this is we have an algorithm which is much more specific. So we're not saying it's just the solution to the empirical risk minimization problem. We're saying it's something that tries to minimize that problem by taking, say, T iterations using a very specific algorithm like stochastic gradient descent with step size 0.3. So we're being much more specific. And the nice thing is that now we're sort of tailoring our analysis to what we're using exactly. So it's much tighter. We don't need to assume we find a global minimizer or anything like this. You know, so if we change any details of the method, we have to update our analysis, but this could be good or bad depending how you think of it. So this main way of thinking, using stability for these bounds, was started around 2002 by Bousquet and Elassif. The idea of applying it to stochastic gradient descent and getting results, at least as far as I know, was, you know, the most influential paper was this Hart, Recht, and Singer paper from just a few years ago. And of course, all these things are continuously being updated. There's more recent bounds on these things from very recent works. So let's talk about, what do I mean by stability? There's different ways to define stability. The one we're going to use in this talk is a notion of uniform stability, or in fact, uniform stability in expectation. This expectation is because my algorithm is going to be a randomized algorithm, like stochastic gradient descent, that has its own randomness. So I say an algorithm A is epsilon uniformly stable in expectation if for all data sets S and S prime of the same size M that differ in at most one example. So that's the perturbation. So this is kind of discrete perturbation. Then I have this result. So it's uniform in the sense that I'm taking the supremum over all possible testing values Z of the expected loss over the randomness in my algorithm of running one algorithm with the data set S and the other with the data set S prime. In general, I want this thing to be small. I want it to be stable. I want this thing to decay as M gets large. Usually something like order 1 over M. And this makes sense. Like if I have two data sets of M examples, if they differ in one point, if M is very large, differing in one point is not a big deal. So I'd expect this thing to be small. Of course, if M is small, then it is a big deal, and this thing won't be so small. And then from there, we can prove a theorem. This theorem is improved in different forms by several works. It's a fairly simple theorem. And it says, if I have a loss function, let's assume it's bounded, then if I'm uniformly stable, then with probability 1 minus delta, I can say the true risk is bounded by my empirical risk plus this term right here. Okay, so this is very nice. This is something I can minimize in practice. This is something I can't do. I can't see this in practice, but I have a theorem that guarantees it's close to this with some probability under these assumptions. Okay, so this is our main theoretical tool we're going to use. Okay, so the way I'm going to use it is my algorithm A is going to be stochastic gradient descent running for T iterations. So now I'm going to write WT to mean the output of my stochastic gradient descent after t iterations. So just plugging in this theorem up here, I get this bound right here. And this term right here, suppose my stability term decays like 1 over m, then this term here is a constant. And so I just get some constants over 1 over m in the square root. So I get this thing right here. And this thing means that as I run with more and more training examples, I can guarantee that this thing decays. So my generalization gets better and better and better as I have more training examples, right? So if I fix t and I have more data, then I can guarantee that my empirical risk is a better proxy for my true risk. Okay, so this is the main idea, and now we can analyze it in two different parts. One is this part right here. I just analyze the stability, so I have to analyze that. And then this part right here is just my usual convergence. And we know, there's a lot of people who work on convergence for deterministic or any kind of, so I said it's a deterministic objective, even though it's a randomized algorithm. Okay, so we can analyze that as well. Okay, so here's a theorem. This theorem is from their work in 2016, which says this variant is without assuming convexity, a batch size of 1. It says if I have a bounded loss function with these smoothness assumptions, that's Lipschitz and the gradient is Lipschitz, then I run stochastic gradient descent for t iterations with this step size, then it's uniformly stable in expectation, exactly this definition we have here, with a bound on the constant that looks like this. So at first glance, it looks like a 1 over m bound. So that's very nice. We do have to be careful. You can't let t depend on m, because then it sort of comes into here and interplays in a different way. So this is sort of for small t, this thing is true. So this was a nice result because it says we're stable if we fix the number of iterations t. The way they prove it, I'm not going to give you details of the proof, but the high level idea is that they think of like two parallel universes. So we have two different data sets, S and S prime, that are the same exact, except for one data point is different. And then we iterate along. In our stochastic gradient, we take a mini batch of size 1. So it's actually going to be quite a while before I sample that data point that's different. So most of the iterates are going to sample the same data point, and then eventually I'll sample a different data point because my two data sets differ in that one point. So we say there's a burn-in period where the sampling is identical and the two tracks of the algorithm are actually identical. Then when they start to diverge, things are not too bad because we have a decaying step size, so we don't actually go too far away. Okay, so this is the result. And I guess the two takeaways are that the dependence on m, as m is larger, this thing gets smaller. That's nice. That's what we want to see. But as we increase the step size t, our stability bound gets worse. So if we only take, suppose we take 0 iterations, that's a very stable algorithm because it doesn't depend at all on the data. Now, of course, that's going to have large optimization error, but that's the kind of trade-off we're going to see. Okay, so let's put that together. I talked before about this bias-variance trade-off here, where I decompose the error into these two terms here, and we have this trade-off. Well, now let's do the same thing, the same error term, but decompose it differently. So I'm going to now decompose it as the true risk minus the empirical risk. And I'll call this the generalization error. And that's what we just talked about. I can bound this generalization error, so this is my epsilon term for the generalization error, by my stability. So if I have a nice stability bound, this thing will be small. And this is going to force me to have small iterations t, because as t gets large, my stability bound goes to infinity. So this thing goes to infinity, hence my generalization bound goes to infinity. Okay, so you can plot that here in this purple. As I have more and more iterations of stochastic gradient descent, my generalization bound gets worse and worse and worse. And that's not good. On the other hand, I have a trade-off, the optimization error here. For this, my optimization error goes down the more iterations I take, so I want a large t. So this is my usual training error. As I take more iterations, this thing goes down. And then if I add these two functions, I get the overall error. And you can see there's a sweet spot for a fixed size t. Okay, so if I have bounds on both these terms, I can then minimize that bound and find a good value of t to run for. And that's our goal, okay? So that's what we're trying to do. So in the analysis, in the paper I wrote, we changed things a little bit. We changed up assumptions a little bit to make things slightly more realistic, we think. But we also want to do things like we want to explain this early stopping phenomena. The fact that you should not run stochastic gradient descent forever. You should stop it early, usually, and that will improve your generalization. Okay, so we're going to try to do that by balancing these two terms and solving for the optimal point, iteration t. And furthermore, it'd be nice if we have results with high probability, not just an expectation. Okay, now the key tool we're going to use for our analysis is this Polyak-Lojasiewicz inequality, this PL inequality, which is this inequality right here. And it says that if you can bound the size of your gradient, it bounds how suboptimal your function objective value is. This comes up because if you're strongly convex, it implies the PL inequality, but you don't have to be strongly convex. In fact, you don't even have to be convex at all. It's nice because if using just PL, you can prove gradient descent converges at a linear rate. So for example, this objective here, our simplest objective you might think of, it's quadratic, it's convex. If A is overdetermined, this is strongly convex and gradient descent converges at a linear rate. If it's underdetermined, it's not so easy to prove gradient descent converges at a linear rate, but in fact it does after a while. So you can prove that using the PL inequality. The PL inequality, so it's looser than being convex or strongly convex. It's more awkward to work with because if F and P are both PL, F plus P is not necessarily PL. So that's annoying, right? With convexity, that is true, but not with PL. And for a similar reason, it doesn't play well with constraints. Okay, so those are some disadvantages. Why, I should point out, it's been quite popular in the past, say, 8 years. There's a nice paper that kind of summarizes many results over here. There's been a lot of different weaker notions in the strong convexity that have been discussed in the past 20 years. And a lot of them are very similar ideas. So why do we assume PL? We're going to assume PL. We're going to do that because it lets us prove we can converge to a global minimizer. And it's somewhat the weakest assumption you can think of that lets you prove that. It's a bit more realistic than strong convexity. It's maybe not that realistic, but it is more realistic than other assumptions. There's also, some work recently showing that if you have a wide neural net, then locally your empirical loss is PL with this following constant. Now, this is actually not super good. We want our constant mu to be as large as possible. This decays with the number of data points you have. That is kind of a problem. We're not going to worry about that right now. A nicer analysis would take that into account. For now, we're just going to think of mu as a fixed number, perhaps very, very small, but still fixed. Okay, so let me summarize our results before we wrap up. We're going to assume our loss function is Lipschitz. It's smooth enough in that it has this PL inequality. And we're going to make an assumption about the gradients that we take. I'm not going to discuss that, but it's in the paper if you're interested. I'm going to define this condition number, very similar to the standard condition number you might see in optimization, and in fact related to the same condition number in linear systems, which is just the Lipschitz constant of the gradient over the PL constant. To simplify the theorem, the statement, I'm going to assume this thing is larger than 1 by quite a bit. And our first theorem says with the following step size, so we're going to decay the step size, and it's a small enough constant. Then if I take this many iterations t, and I chose this t in order to balance the generalization error and the optimization error. So I choose t to balance that. Then I have the following result in expectation, that this thing converges at the following rate, which looks like 1 over m, but m has this exponent depending on the condition number. Okay, so this means for any k non-zero, or sorry, for any kappa that's strictly non-zero, then this thing at least decays as I take more and more samples. So that's good. And furthermore, we have a different variant of the theorem, which says similar assumptions, slightly different numbers. That says if I do the same thing, but now I can actually show that this thing holds exactly, but with probability 1 minus delta. And I pay a price of putting this 1 over square root of delta in here. So it's like a Chebyshev Markov kind of thing. We do have a version that only has a log delta, so it's a high probability result, but it's much more subtle in that regime based on the size of the step sizes and how much data you have. So I'm not going to talk about that too much. But the bottom line of these results is that if you choose the right number of steps, t, then you can show that your true risk converges to the best it can be. Okay, so that's what we want. If I get more data points, I can do as well as anybody could. The main ingredients in the proof are a high probability bound on stochastic gradient descent, assuming the PL inequality. So there's a few subtleties there. Then we can use a standard stability implies generalization result, like I showed you here. And then we have these two competing terms, and we just trade off t to balance those two terms. Okay, so let me sort of summarize at least my takeaways from working on this. Assumptions, which I've somewhat gone over a little fast in this talk, are actually quite complicated, and it's easy to get yourself in trouble by assuming things that are contradictory or lead to vacuous results. Not just assumptions on, say, smoothness or differentiability or things like that, but assumptions on how many steps you take and on the size of t compared to the number of samples m you have. So that's, you can get yourself into danger there. Some results you see in the literature that might appear nice, but then they actually might be vacuous depending on how these assumptions can happen. We use PL, which is, I say, is slightly more realistic than standard convexity. We used stability, and I'm not sure this is the right way to go, but I think stability is a nice tool because it lets you ask very interesting questions like, if I have two methods, one converges faster than the other on a general objective, so the training error goes faster. You know, think of Newton method converges faster than gradient descent. Not worrying about how much an iteration costs, but just in terms of iteration count, it converges faster. But that's maybe it's less stable, so there's a price to pay in stability. So there's a nice trade-off there, and you can ask which methods converge fast and are stable. And those are the ones that are going to have a small testing error, or a small true risk. So I guess the big point is in optimization, we care about the actual loss function. And that's not what you care about in machine learning. You care about the actual true risk, the testing error. So we can't pay too much attention to training error when we really care about testing error. Okay, so that's all I have. We have a preprint online if you want to see the details, and I'm happy to take questions.
Yeah, so are there any questions in the audience? Maybe just unmute yourselves if you have the rights, or write in the chat. Well, in this case, I think I'm just going to go ahead. Well, first of all, thanks, Stephen, for the very clear talk and a very good overview over the role of stochastic gradient in deep learning. How are there any genericity results in terms of if you converge to a certain point with stochastic gradient on a neural net, that, well, let's say the Hessian or the like Clark generalized Hessian is positive definite, or is that a question that doesn't even arise?
Right. I think no one asked that because I don't think you can test it empirically, because I think these things are big enough where you can't even sample a gradient. Oh, you can't even get the true full gradient. You have to sample it. So any kind of estimate of the Hessian, right, not worrying about non-differentiability, even if you're differentiable or C2, you couldn't, I don't think you could estimate that. So I don't know if people know if that's true or not in practice. And so, yeah, I don't know if that's been asked, but you know, I don't know if you do.
Okay, and so another thing that I was wondering, I mean, the PL property kind of weakens the strong convexity assumption somehow, but it seems like nobody's getting away from the L smoothness, or in your case, beta smoothness. Is that always satisfied in these settings, or is that a strict assumption?
No, I think it's a fairly strong assumption. I think the way to get around it is assuming everything's bounded. I mean, if things are bounded, then everything works. Because if you're smooth, if you're smooth on a compact set, then you have, whatever you want. But yeah, so I think people need to show that these things are bounded in practice. And for example, for our analysis with the PL, we can't incorporate a projection step onto a compact set, because that ruins the properties of the PL function. So that's a problem for us. With strong convexity, you can do that. But yeah, these things are all sort of contradictory unless you're on a bounded set. And so then enforcing that you live on a bounded set then is sometimes a problem. So some people can get away with that, but with PL, that's kind of hard to deal with.
Right. And so are there now any questions from the audience? Please feel free to ask them as long as we're here. Maybe then I'll ask just one more question. So that's maybe playing devil's advocate a little bit. So if I was an approximation theorist from 50 years ago, I mean, what's really now so much different than what approximation theorists already did, in a sense? I mean, you're basically trying to, well, solve an approximation theory problem, right? Right.
Yeah, I mean, a lot of things are not that different. I think we ask a lot of different questions, by thinking of like a Weierstrass kind of theorem on approximation. That's very classical, and so that's not really that new, and maybe the techniques are no different than they were, but just the statistical setup is maybe different, right? So in numerical analysis, we don't often put a prior on things, and it's kind of weird here because we're not really Bayesian, but we're still statistical. So it's this sort of nice in-between realm that's somewhat reasonable. In the real world, IID assumption is maybe not true, but it's a nice framework. So I think maybe the questions we ask are the most different part than from 50 years ago.
I think what we should do now is we stop the recording, and maybe Stephen, if you have time to hang out a little longer than like 10-15 minutes, sure. I would certainly be happy to chat a little more, and then whoever is interested could just stay here and chat for a bit, and maybe turn on the cameras also.